we're going to continue our discussion of how to write electron configurations. And before we begin, just to emphasize again the key idea behind writing electron configurations. If you read it properly, the periodic table itself is going to give you the electron configuration for every element on the table. There's a couple of exceptions to that, not significant for our course. So mastering this idea of how to use the periodic table to give you the answer that you're looking for is paramount. Just a review of the rules for writing electron configurations that we discussed in the previous video. Rule number 1, maximum of 2 electrons can fill any single orbital no matter what the type. Rule number 2, you fill orbitals of lowest energy first before moving to the next available and highest energy orbital. So you fill orbitals in order of successive increasing energy of those orbitals. And rule number 3, electrons will occupy orbitals of the same energy singularly before pairing up. And it's the orbital diagram, when we get to that, that will give us the best understanding of rule number 3. So we're just going to put that rule on pause until we get to this portion. So in addition to knowing the rules for writing electron configurations, it's very important that you understand when you look at a periodic table where the S block elements are, representing elements whose last electrons are going into an s orbital, where the p block elements are, where the d block elements are, and where the f block elements are. Remember, there's only one s orbital in any energy level. It holds a maximum of 2 electrons. So this section here with 2 columns to it represent the s orbital elements. The last electrons entering into any element in this s block are going into s orbitals. Then over here we have a grouping 1, 2, 3, 4, 5, 6 columns across. Recall that there are 3 p orbitals in every energy level beginning with the second and higher. 3 p orbitals, 2 electrons can occupy each one for a total of 6 electrons needed to fill the p orbitals of any energy level beginning with the second. So this set of 6 columns represents the p orbital elements. Last electrons occupying orbitals for these elements are going into p orbitals. By similar reasoning, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we're in the d block elements. 5 d orbitals, 2 electrons can occupy each for a total of 10. When you are looking at the d block elements, also known as the transition metals, the last electrons entering these elements are going into d block elements, or excuse me, d block orbitals. And then finally we have our lanthanides and actinides. Remember that lanthanum and actinium belong up here in the tables that I am most familiar and comfortable using. And this table indicates there's kind of a gap there and see below. So if you cover up lanthanum and actinium and just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, you see that you are in the f block elements. F orbitals come in a set of 7, 2 electrons in each for a total of 14 electrons needed to fill f orbitals. When you look at the elements of the lanthanides and actinides, the last electrons filling those atoms are going into f orbitals. So putting together the SPDF orbitals with the idea that periods represent the highest energy level being filled, you can now put this information together and see an order of filling. First you fill the 1s. with 2 electrons. And we can imagine for a moment that helium sits here. It belongs with the noble gases, but for the purposes of our discussion here, first energy level, 2 electrons, they go in a 1s orbital. Then you fill the 2s orbitals, then the 2p orbitals, 3s orbitals, then the 3p orbitals, 4s orbitals. Pause, we're in a d block, but that first set of d orbitals is in the 3rd energy level. So the d orbitals are always present in the energy level 1 below the valence energy level indicated by the period number. 4s2, 1 below 3d10, back to the 4th energy level, 4p6. 5s2, 1 below 4d10, 5p6. 6s2, and then hold on, this period is trying to help with a common mistake. You don't just immediately blast through the 5d orbitals. The table actually says, wait a minute, there's a split or a shift in atomic numbers, 55, 56, lanthanum is sitting right here, 57, and then boom, hafnium 72. Wait a minute, there's a gap. This table should be split, and the lanthanides and actinides inserted in. So 6s2, now we jump down to this first column of lanthanides. We're in an F block. First energy level to have F orbitals is the 4th. So you're way up in the 6th energy level as valence, 6s2, before you come down and complete the orbitals of the 4th energy level, 4f14, then come back. Now we're back in a D block, one below, sorry, this D block, don't get lost here, 4f14, come back. We're in a D block, one below valence, 5d10, 4p6, and then we rinse, repeat. 7s2, there's going to be a gap, jumping down, 5f14, coming back, 6d10, 7p. There we have it. Let's see if we can put that together and review some specific electron configurations. Let's take a look at the oxygen family, family 6A. Now, I'm old school. We were taught this information with Roman numerals for family, letters, numbers and letters for the A families, but newer convention is to just use alphanumeric. I don't care what you use, just the right number. Oxygen family, family 6A. And if we take a look at the elements of the oxygen family, the first element is oxygen with a total of 8 electrons. And let's see what the periodic table is telling us for the electron configuration of oxygen. Its atomic number is 8. That means the neutral atom has 8 electrons. And how are those electrons arranged? What is their configuration? Well, 2 go in the 1s orbital, 1s2, and then it is filled. So we start the second energy level. 2 electrons go in a 2s orbital, 2s2, and then we come over here, we see oxygen in a p block. Its last electrons are going into 2p orbitals, 1, 2, 3, 4 over 2p4 is the last part of the configuration for oxygen. 1s2, 2s2, 2p4. Now before you sign off, it is so important that you do this check. Add up those superscripts which represent the electrons that you are trying to account for in the neutral atom. We are trying to account for 8 electrons, so those superscripts need to add up to the number 8. And counting, 2 plus 2 is 4, plus 4 is 8. Bingo, we've accounted for the correct number of electrons in the neutral atom. It's going to get really crowded. In other words, the configuration will rapidly expand quickly as we move through the periodic table. So we have developed an abbreviated electron configuration to help shorten the information down and reveal the most important information. So abbreviated electron configuration for any element. You locate the element, you move to the noble gas element that directly precedes it, comes before it, which is helium in the case of oxygen. You put helium symbol in brackets, and then you write only the electrons that come after helium as part of the abbreviated configuration. 2s2, 2p4 for oxygen. So it's abbreviated configuration using the noble gas element helium. Helium 2s2, 2p4. What that means is the 1s2 configuration is that of helium, and you are just writing everything that comes past that. Oxygen has an inner configuration like helium, and its valence energy level. That's an important term. Valence means outermost or highest energy level. Its valence energy level is the second. That's why it's underlined, and it has a total of 6 valence electrons, 2 in an s and 4 in a p. You can also give a picture, which we call an orbital diagram, to represent the abbreviated electron configuration for an element. Notice that the abbreviated electron configuration is always what is used for an orbital diagram. Don't try to use a complete electron configuration. I'm exaggerating, but you'll spend days writing boxes, and that is not what we're interested in. We just want to get the essential information. So you always use the abbreviated electron configuration for an orbital diagram. So we put helium in brackets, and we use boxes to represent all types of orbitals. We know orbitals are not shaped like boxes. This is an accounting tool, right? The boxes are merely a representation, a bookkeeping tool for the number and type of orbitals. If there is a gap between the boxes, that gap represents a difference in energy. So the 2s orbitals are lower in energy than the 2p and will fill first. If boxes are attached and not separated, they are of equal energy. And now we get to illustrate that third rule used to write electron configurations. Right? Our configuration for the abbreviated configuration shows 2 electrons in a 2s. Those 2 electrons are paired up. I'm representing them with arrows. Let me remove that less than sign just for a minute so it's not so crowded. I'm using arrows to represent electrons, and I'm showing an arrow up and down. What is the significance of that? Not something that I'm going to stress in this class, but essentially electrons have spins associated with them, and when electrons are paired up in the same orbital, they spin in opposite directions. And that opposite spin generates magnetic fields with orientations in opposite directions, North Pole, South Pole. So we know that a negative charge and a negative charge repels, but spinning in opposite directions and generating magnetic fields that are oppositely oriented creates some attraction. North Pole attracts to South Pole. So it kind of helps them tolerate having to share the same room, so to speak, to have opposite spins. That's the meaning of the arrow up and down, not something that I'm planning to test you on, but helpful as you look at this diagram to understand it. So 2 electrons paired up in an s orbital, 4 electrons are occupying the p orbital. The last rule of writing electron configurations is that electrons will choose to occupy orbitals of the same energy singularly before pairing up. So we're placing 3 electrons in these 3 separate 2p orbitals 2px, 2py, 2pz. They'll choose to occupy, they want their own room, so to speak, because of that electron-electron repulsion. But the fourth electron chooses to pair up rather than having to move to an even higher orbital, higher energy orbital, and get a lesser view, less exposure to the nucleus. So this fourth electron pairs up before moving to a higher energy orbital. So looking at our orbital diagram, we see that we have a total of 2 unpaired electrons. And that number of unpaired electrons gives us helpful information for bonding, which we'll talk about later. And it is also associated with the property of magnetism. If an element exhibits magnetic properties, that means it has 1 or more unpaired electrons. Let's go ahead and take a look at the next member of the oxygen family, sulfur, and see if we can't get the configuration for sulfur understood. It's written up on the board, but let's see if we can't get it figured out ourselves before we look at what is written. So here is sulfur. In the oxygen family, atomic number is 16. 16 electrons in the neutral atom. And what is the electron configuration for sulfur? 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4. So the last electrons for sulfur are entering into p orbitals in the 3rd energy level. Sulfur is 1, 2, 3, 4 boxes over in the p orbital section, meaning that there are 4 electrons filling those 3p orbitals for sulfur. So let's write down what that configuration is that I just read with you off the periodic table. 1s2, 2s2, 2p6, 3s2, 3p4. Before you do anything else, once you write that configuration, you add up those superscripts and make sure that you are counting for the electrons present in the neutral atom. Running total, 2 plus 2 is 4, plus 6 is 10, 12, 16 electrons we have accounted for in our electron configuration. Valence energy level for sulfur is the 3rd. That is the highest energy level with electrons present in it. Writing the abbreviated electron configuration for sulfur. Back to our periodic table. We look at sulfur, back up to the noble gas that precedes it, put its symbol in brackets, and then write what comes after. So neon bracketed 3s2, 3p4 is the abbreviated electron configuration for sulfur. Neon 3s2, 3p4. So we see that this is giving essential information to us that we will use later on. Valence energy level is the 3rd, 2 electrons in an s, 4 electrons in a p orbital. Looking at the orbital diagram, filling in the boxes. You could be asked to draw an orbital diagram. You use boxes to represent orbitals. Make sure you label the boxes, that you include the noble gas element that is part of the abbreviated configuration. You're always using the abbreviated configuration for an orbital diagram. 3s2. So arrows representing electrons spinning in opposite directions, arrow up, arrow down. 4 electrons in these 3p orbitals using the 3rd rule of electron configuration, also known as Hund's rule. Electrons occupy orbitals of the same energy singularly before pairing up. So I have 3 electrons here singularly, and that 4th electron then pairs up. So we see that once again, we have 2 unpaired electrons for the orbital diagram for sulfur. At this point, I invite you to pause this video and you yourself write the complete electron configuration for the next member of the oxygen family, selenium. Its atomic number is 34, and the neutral atom has 34 electrons in it. So why don't you pause this video and write the electron configuration for selenium yourself, then get the abbreviated electron configuration, and then draw the orbital diagram. Alrighty. I hope you've taken the time to do this work on your own, and let's see if you are seeing the same thing that I am seeing when looking at the electron configuration for selenium. So putting this periodic table back up, right, and doing our count here. And somewhere, here we go, is a pencil to help me kind of point the way. First we fill 1s2, then 2s2, then 2p6, 3s2, 3p6, 4s2, pause. We are in a D block, but that D block, first time we've encountered it, is one below the fourth energy level. D orbitals are encountered in the third energy level first. So 4s2, 3d10, 4p, back to the fourth energy level. P orbitals and S orbitals always belong to the energy level associated with the period number they are in. So 4s2, 3d10, 4p, 1, 2, 3, 4. 4p4 for the last electrons filling selenium. And notice we're beginning to see a pattern here with this 4p4. That is something that's key to understanding the overall organization of the periodic table. So writing down what we just wrote, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. We just spoke that electron configuration, and now we're writing it down here and confirming it, the complete electron configuration. Let's do a running count of those superscripts. 2, 4, 10, 12, 18, 20, 30, 34. And that's exactly the number of electrons that we are trying to account for in selenium, 34 electrons. Abbreviated electron configuration for selenium is backing up to argon, putting that in brackets, and then whatever comes after that noble gas. So selenium has an inner core configuration like that of argon, and then we express 4s2, 3d10, 4p4 for the last outermost electrons for selenium. So selenium's abbreviated electron configuration, argon, 4s2, 3d10, 4p4. Notice even though these 3d electrons are appearing, they are not considered valence. The valence energy level for selenium is the fourth energy level, and there are 2 electrons in an s and 4 electrons in a p orbital in the fourth energy level for a total of 6 valence electrons, making these valence electrons pop a little more. So here is the abbreviated electron configuration for selenium. Fourth energy level is valence with a total of 6 electrons. That's exactly the same pattern of valence electrons that we've been seeing for sulfur and oxygen. And we see a similar pattern for how those 6 valence electrons are arranged. 2 of them are in an s orbital. D orbitals are there, but they are not valence. These d orbitals are filled with 10 electrons, and notice I fill them using Hund's rule, filling them singularly before pairing up. And then we have 4 electrons in the 4p, filling those orbitals with electrons singularly before pairing up. So I'm seeing a pattern here with a valence configuration of electrons, same number and arrangement. We have 2 unpaired electrons for sulfur, 2 unpaired electrons for selenium. And then I'm going to do something that I always appreciated as a student when a teacher did this for me. I'm going to do one last example that is the most lengthy. I never appreciated when teachers did easy examples for me in class and then gave me something really hard on a quiz or an exam. So tellurium comes next, but we're going to skip over tellurium and head for polonium. It is still in the same family, and there are 84 whopping electrons that we need to account for in a polonium atom. So put your video on pause and see if you can use the periodic table to write the electron configuration, complete electron configuration for polonium, and then write the abbreviated electron configuration. So why don't you pause right now and do that. Alrighty, I hope you've had an opportunity to write down information on your paper, and let's see if we're seeing this the way the periodic table is revealing it. What is the electron configuration of polonium? Where do those 84 electrons go? How do they occupy the orbitals surrounding the polonium nucleus? First 2 electrons go in a 1s orbital, 1s2, 2s2, 2p6, 3s2, 3p6. This order of filling that we're beginning to find this rhythm with. After you fill the 3p orbitals with 6 electrons, then you fill the 4s with 2 electrons. So 4s2, D block, it's the 3d, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, right? Remember what we said here, this little gap and shading is telling us, wait a minute, watch out, don't be caught off guard. We technically would just start the 5d orbitals with 1 before we jump right down to the 4f, encountering an f orbital for the first time. So since I know I'm going to have to come back, I kind of just say 6s2, 4f14, 5d10. And I'm almost home. I'm in a P block. Here is polonium. 1, 2, 3, 4 columns over. 6p4 is the last part of the electron configuration. And that's a lot to write. So let's see if I got this here. 1s2, 2s2, 2p6. It's helpful to have a periodic table right in front of you as you're writing this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. I'm running out of room, coming to the next level. 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p4. Before you pass go, before you collect $200 to use that very familiar Monopoly analogy, make sure you're counting those superscripts and it adds up to 84. So here we go, running total, 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, plus 14, pausing is 70. 70 plus 10 is 80, plus 4 is 84, and bingo, that's the electron count we need. 84 electrons in the neutral polonium atom. But who wants to write all of that? So this is where that abbreviated configuration is very helpful. looking at polonium, backing up to the noble gas that precedes it, which is xenon, and then writing only what comes after xenon. So polonium has a core electron configuration like xenon, and then writing what comes after that, 6s2, 4f14, 5d10, 6p1, 2, 3, 4. That will be our abbreviated electron configuration, xenon, right? So everything up through here is the configuration of xenon. And then we write just what comes after. 6s2, 4f14, 5d10, 6p4. Our valence energy level is the 6th energy level. That's the period that polonium is found in. So valence energy level is the 6th, and we see we have 6 valence electrons, 2 and an s, 4 and a p. The orbital diagram for polonium is going to be the lengthiest. You have to write the noble gas and then boxes representing the orbitals for everything that comes after the noble gas core configuration. So one box representing the s orbital in the 6th energy level, 7 boxes representing the 7 orbitals that are in the 4th energy level, 7f orbitals, let me be specific, in the 4th energy level, 5 boxes representing the 5d orbitals that are in the 5th energy level, and then 3 boxes representing the 3p orbitals in the 6th energy level, which is valence. So 2 electrons in an 6s orbital, and they have opposite spins. My boxes are crowded. 7 f orbitals, each holding 2 electrons, and it's gonna be crowded here. Right, so there we go, trying to represent 14 electrons in those 7 4f orbitals. 5d orbitals are also filled. There are 10 electrons, 2 in each box in those 5d orbitals. 6p orbitals are not filled. There's only 4 electrons filling singularly and then pairing up with that 4th electron. So the 6p orbital is not quite filled. 2 more electrons can enter in, and there are a total of 2 unpaired electrons. For polonium, exact same pattern as we've observed with the other members of the oxygen family, family 6A. And now we get to, for me, the really good stuff. What has all of this shown us? Well, we now have insight into the periodic law. There is a repeating pattern to the physical and chemical properties of the elements, right? So a repeating pattern to the physical and chemical properties of elements when arranged by increasing atomic number. That's what Mendeleev used as a principle for organizing his table. Elements with similar properties were placed in the same family or group. But if you had asked Mendeleev back in like 1869, why are elements showing a similar repeating pattern, he would not have been able to answer that question. And scientists lived and died wanting to know that answer, spending their lives seeking it, and never discovering it in their lifetime because the technology wasn't available to reveal the deeper underlying foundational principles. But we now know. Why is there a repeating pattern to the physical and chemical properties? Our work is revealing this. Elements in the same family have similar properties because they have the same number and arrangement of valence electrons. Same number and arrangement of valence electrons. So for example, the oxygen family has 6 valence electrons. Same number of valence electrons, which is 6, right? So same 6 valence electron count, and those electrons have the same arrangement. 2 electrons in an ns, meaning N is the valence energy level, so 2 electrons in an s valence orbital, and 4 electrons in a p valence orbital. So same configuration. So big idea here. If you are looking at a representative family, these are the families with the A letters with them. So one more time, representative family, 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. If you are looking at any of these A lettered families, the number associated with the letter A is the number of valence electrons. So oxygen family, family 6A, has 6 valence electrons. And using a smaller periodic table, carbon family is family 4A, and it has 4 valence electrons. So any element in the carbon family, you don't even have to write the configuration, just look at that number with the A letter, and that tells you the number of valence electrons for all of the elements of that family. Alkali metals, 1A, 1 valence electron. Alkaline earth metals, family 2A, 2 valence electrons. Halogens, family 7A, 7 valence electrons. Noble gas, family 8A, 8 valence electrons, with the exception of helium. So let's take it to a quiz question. Suppose I said on a quiz, which element or elements of the periodic table are most similar to the element sulfur? Well, if I asked you which element or elements on the periodic table most similar to the element sulfur, that answer would clearly have to be either oxygen or selenium, because they are in the same family as sulfur and most closely adjacent to it. Right, so notice as you move down a family, although there's similarities, there are changes, like on a paint chip card. If you've ever seen a paint chip card with little fragments of, say, blue paint, they're usually listed in increasing intensity and darkness of blue, so that that bottom chip color may look very different in terms of shading than the top chip color, but you see a pattern in terms of how that shifting is taking place. So there are similar properties, but also shifting as you move down a family. Any element in a family, the elements most closely surrounding it are the ones that it is most similar to. So either oxygen or selenium would be most similar to sulfur, and the reason is because they all have 6 valence electrons, 2 in an s orbital and 4 in a p orbital.